Well, let's come back to chapter 2, and I hope we'll finish chapter 2 today. And last time, I derived the Schrödinger equations and show you that this real space and momentum space wave functions are related by the Fourier transformations. So today, we will continue going this line to interpret this Schrödinger wave function within the probability framework, and we will define the probability current and define this expectation value that we can calculate to observe physical quantities in quantum mechanics. And we will derive very useful equations for us to calculate the momentum-dependent observables, and we will show that there is a commutation relations between the momentum operator and position operator. Okay, but before that, let's just go back to this Heisenberg uncertainty relations. In the different example in the textbook that we investigate the Bohr's orbits. You know, the Bohr theory is kind of a semi-classical way to understand quantum mechanics. So the Bohr said these electrons are circling around this nucleus in this classical type of orbits, but carrying a characteristic angular momentum, which is quantized. And that's what this Bohr theory is telling us. However, as I mentioned, electrons never circle around this circular orbit around this nucleus because the electrons are distributed within the Schrödinger formulation and can be calculated in the probability distribution. So there's no way that you could really see the electrons circling around this nucleus in this kind of orbit. So you could try to locate these electrons in any orbit, but of course it's not possible to do so. Okay, and this example is exactly telling you that it is not possible to actually try to find the exact location of the electrons circling around this nucleus orbits. Suppose there's two Bohr's orbits labeled by quantum number n and n plus 1, where n plus 1 is actually located further from the nucleus compared to this orbit labeled by quantum number n. And you know that this radius or distance of any Bohr's orbit, relative to the center of the nuclear core is inversely proportional to, it is proportional to this n squared. Okay, and so the energy of the Bohr within Bohr theory is actually proportional to 1 over n squared. So you know that. So the question is whether we could know exactly which orbit that the electrons are moving around. So if we need to know which orbit electron is, then we need to resolve this distance between this radius labeled by quantum number n and n plus 1. Meaning we need to send a laser to actually detect these electrons in this nth orbit. But that wavelength should be much shorter than the distance between these two radius, Rn plus 1 and Rn, right? So how do you see this electron? Okay, so you don't see electron by your eyes. So you send a laser, you send a particle, you send a photon. You hit this electron, and then you see this electron that kick out of this incident photon, and that's the way that you detect the electrons circling around a particular orbit, say the nth orbit. But the wavelength to really resolve that distance between this Rn and Rn plus 1 should be much shorter than the distance between these two, the difference between these two. Right? So this is the resolution, spatial resolution. So you need to have a much better spatial resolution to see whether this electron is in the nth orbit or the n plus 1 orbit. Okay? So if you hit these electrons by a light carrying the wavelength lambda, and this lambda must be much shorter than the difference between these two radius, Bohr radius. But what is this? Which is within the Bohr theory, which is, roughly speaking, proportional to n. So you could simply just simplify these differences between these two n squared and n plus 1 squared, and in the limit of n goes to very large value, and this is roughly the estimation of this upper bound for this lambda. And lambda should be much smaller than that value. However, if lambda is that bounded by this value, which means that this momentum of this photon should be much greater than this h over lambda, because this is the relation by de Broglie. De Broglie says that momentum of a quantum particle is given by h over lambda, where lambda is de Broglie matter wavelength. So this momentum of photon should be much greater than this, and this is so-called momentum transfer. So this momentum is the momentum that's carried by the incident photon to hit this target electron, right? So this momentum p gamma should be much greater than that value, okay? So this is called momentum transfer, but that momentum transfer is really, really huge, which means that you need to really hit your target by a very high energy, high momentum photon beam, and this leads to an energy change to your system by that amount, roughly speaking, because this is the energy change or external energy injection. So delta E is the energy change that is due to the introduction of the photon beam. Okay, so this energy is the extra energy that hit these electrons accompanied by this photon beam. Okay, so this energy shift is really, really huge, which is much greater than this value. Okay, so delta P is your momentum transfer, that is external momentum change that introduced when you hit the target by the photon beam. So you just plug in this delta P as P gamma right here, and you plug in this lower bound of your delta P, and as a result, there's an energy change or energy increase or energy injection during these processes, and this energy injection is that much, at least. It's much greater than that amount. What does it mean? It means that if you really want to see which orbit the electron is circling around the nucleus, you must send in a very high energy photon beam, and that energy is much greater than this value. Okay? But what is the value? Okay, this value is nothing but the energy of that electron in that Bohr's orbit. So you know, as you can check your chapter 1, your textbook, that in Bohr's theory, energy of a specific Bohr radius is given by 1 over n squared times some prefactor constant, and this is precisely the value, the absolute value of this energy of the Bohr's orbits for n's orbits. Okay, which means that your external energy is going to destroy this electron, because this energy is enough to actually kick this electron out of its orbit. So this electron, delta E, is large enough to kick this electron out of its nth orbit. Okay, so then you are dead. Why you are dead? Because it contradicts your original purpose. Okay, so your purpose is to see if this electron is in nth orbit. And to do so, you must send in the highest resolution photon beam to hit your electron, and then you see this electron, right? But in order to resolve this tiny difference or radius and between this nth orbit and n plus 1 orbit, this photon beam is really high energy. And this high energy injection of a photon beam to resolve which orbit that electrons orbit around nucleus is really large enough to destroy this electron. Okay? So, and this is precisely that you want to avoid. So, which means that you want to see this electron, whether it's here or there, but when you want to see this electron, you must kick out of the electron, and you don't see this electron anymore. You want to see this electron, but the energy carried by this photon beam to really detect the electron is large enough to really kick out the electron. And as a result, there's no way to really exactly know which orbit for any electron is located. And this is a very good example showing you that really Heisenberg uncertainty relation governs all quantum mechanical phenomena. And this also tells you, although it's a bit counterintuitive, but this is a very important message to all of you that what is really observed in quantum mechanics. Okay? In quantum mechanics, we must go to the atomic level to really detect or really see or really observe any phenomena. Okay? So we don't use our bare eyes, we don't use a detector. Of course we use a detector, but the principle that governs the detection by any detector is also governed by quantum mechanics. Okay? So even the classical detector, so at the very deep down, it is also governed by quantum mechanics. So you cannot escape quantum mechanics. No matter how smart you are, if you would like to design a clever, a smarter way, a smarter detector, okay, so you name it, you could go ahead, but one way or another, you are going to face the same problem, the same trouble that forbids you to really detect exactly the location of any quantum particle if you want to know at the same time the wave property. So the wave and particle properties cannot be detected at the same time. All right, so more examples that we will see later following the same logic that Heisenberg uncertainty relations governs all this troublesome counterintuitive phenomena, but it is true that this phenomena is really what you will see in experiments. Namely, you don't really locate the exact position of electrons circling around the nuclear core. What you really see is the probability distributions, the s orbit, the p orbital, and the d orbital, and so on. So these are all probability distributions. So you never really know exactly the location of that electrons. You only know the probability distributions. So now I guess you must be used to this kind of argument, and this argument will actually continue as we discuss more and more quantum mechanical problems. Okay, so for those of you who have not taken this modern physics, please read and study chapter 1 carefully, because many of these notations that I use could be found in chapter 1. For example, this alpha is called fine structure constant, which is 1 over 137, which is a constant you should know. And what else? H and H bar, and de Broglie relation, and Bohr radius, and so on. Okay, so all these notations that I use can be traced in this earlier chapters, either in your modern physics textbooks or chapter 1. So I won't repeat that. Okay, so let's just come back to this probability interpretation of a Schrödinger wave function. So as I mentioned, this wave function satisfies the Schrödinger equations, which is nothing but the probability distribution function that you can find a quantum particle in space and time location, and we should interpret this psi as a probability distributions or probability amplitude. So the real probability is really the square magnitude of this psi. So the normalization condition requires that when you sum over all the probability densities, which I call this pxt, so the p is called the probability density function, which is nothing but the magnitude square of this Schrödinger wave function, psi xt. And of course, this is a distribution function, right? So it has some peaks and deep and vanishing at plus minus infinity and so on. Okay, so but we know that if you sum over all the probability density, you must go back to normalized value, which is 1, which tells you that you can always find a particle, okay, in the universe. Okay, so if you try hard enough, and you should always find that particle. So finding the particle in the universe is something that is for sure. Meaning there's a 100% probability to find a quantum particle in the universe. It's not here, it's not there, but sooner or later it will show up. Meaning if you sum over all the probability distribution function, you must find this out. Meaning this normalized value 1 in terms of a probability is 100%. So this particle may be here with a 30% of probability to show up here, and another 40, another 30. So if you simply just sum of all these probability distributions, and this must be 100%. That's really a trivial statement. It's called the conservation of particle. So, and this is a physics requirement. So you cannot destroy it or create a particle for no reason. So that's normalization. And the second property of this probability distribution is that this psi of xt is a square integrable function. So what is square integrable function? So we will use that property later. It is defined by this inequality, meaning in the square magnitude of this psi at any given time, for example, time equals 0, when you integrate over this entire space, should not be infinity. Okay, it should be a convergent value. So this is called a square integrable because this function, this integral, is an integrable integral. Okay, meaning it's not infinity, it's not a divergent integral, and it is square integrable, means that this square of this function is integrable. The square of this wave function is integrable. Okay, so and why do we need the square integrable properties of this wave function? Well, it is needed because we need a proper boundary condition, which means that either in the very far away plus infinity of x, or the other side minus infinity of x, this wave function should vanish. Meaning in the very far in that way or very far away backwards, there's almost no probability distribution of any quantum particle. So quantum particle is distributed within a finite range. Okay, so this is a reasonable requirement, and we will see later that this allows us to really get the physical quantities. Otherwise, there's a chance that some calculations based on the Schrödinger wave function will go infinity or become divergent. And to avoid that divergence, and we know that there shouldn't be any divergence in any physical observables, because anything that we can measure in the lab is a finite valued quantity. Okay, it's always a finite value. So you cannot measure a quantity which is infinity in your lab. And this is the mathematical requirement that all these probability distribution functions of Schrödinger wave functions must vanish either when x goes to plus or minus infinity. And it is called square integrable properties of Schrödinger wave function. And the third property is the phase and interference. As I mentioned, just like a light wave or water wave in quantum mechanics, a quantum particle and its wave and their wave functions could interfere with one another. And the reason why they can interfere is because this wave function is actually a complex value which carried a magnitude and a phase. And when you superimpose these two, say, electron wave functions and add them in such a way that they lead to a quantum interference, because there's a phase factor, theta 1, theta 2, in each of these wave functions. As a result, you get interference. So interference comes from this phase difference between these two thetas, and this Schrödinger wave function psi xt in general is a complex function, okay, which has the real, this magnitude and the phase, or the real and the imaginary part of the wave function. Because of the complex nature and the linear properties of the Schrödinger wave functions, we could have this quantum interference just like waves, electromagnetic waves, or a water wave. And finally, we could define so-called probability current, just like energy flow or the flux in your classical mechanics. We could define the probability current, which is the flow of your quantum matter in the Schrödinger representation. So this can be defined in the following way. So suppose this is the Schrödinger equations. I put the stars here to refer to the fact that this is a complex conjugate of psi, which means that if this psi is A plus IB, then psi star will be A minus IB. Okay, so suppose this probability density P is given by simply just psi square, the magnitude square of psi, then I can take this time derivative, partial time derivative of this probability density, which is this, but we know that this is given by psi times psi star. Okay, so by chain rules, we could just decompose this into different derivative. And for each of this term, you could plug in the Schrödinger equation, and this is the Schrödinger equation for psi star, and you know what this Schrödinger equation for psi. So just plug in this, Schrödinger equations for psi and psi star, and you combine these two Schrödinger equations, you get this. So pay attention to this minus sign here. All right, so good. So then we could just rearrange this term and define so-called probability current. And the stuff inside the bracket is called the probability current, J, xt. And you could just use this definition to rewrite this partial time derivative of probability, P, in a way that this has the same form as so-called continuity equation in your classical mechanics. Okay, so this tells us the conservation of your particle flow. So the time change of a probability density is given by the negative of your spatial derivative of your probability current or flux. Okay, so this is called flux. Let's just take a short break. When we come back, we will draw an analogy between this probability current in quantum mechanics and continuity equation in classical mechanics, describing kind of a fluid flow. If you have some water float, okay, from say left to right, and then you could use this continuity equation to describe such a fluid dynamics. So the time change of your, say, matter that's passing through any surface or tube, a water tube, is given by the volume of that water that's enclosed by the tube. Okay, so we will draw this analogy later, but this is very similar to what you are familiar with in classical mechanics, that the matter or the particle is actually conserved when there is a particle flow, and you could just count the time change of your particle flow as the collection of this volume of your particle moving towards the other end. Okay, so let's take a short break. When we come back, we will tell you about these continuity equations and the quantum mechanics interpretation of these continuity equations. So here we like to formulate and describe the Schrödinger wave functions in a more rigorous and mathematical way so that it gives us a reasonable and physical results which would not lead to any contradictions or some unreasonable results. So this is the mathematical requirement for Schrödinger equations and Schrödinger wave functions to really give rise to physical quantities that can be measured. And as I mentioned, you can consider this probability P, which is a square magnitude of the Schrödinger wave functions, as some kind of a probability flow. Okay, it's like a flow of matter, okay, or flow of water, flow of fluids, and some kind of a matter flow. Okay, because this is the probability of finding a quantum particle. Of course, it's not the real particle flow. This probability flow in quantum mechanics is interpreted as a particle flow, because this is the probability that you can find a particle. So somehow it is related to this particle flow. So let's just take a look at the continuity equations in quantum mechanics. So let's just try to look at this interpretation of this continuity. So to look at this analogy, you could integrate over this entire space of this probability density. Suppose you simply just integrate it on both sides of the equation like this, and then you should see this correspondence. So let's just look at this integral on the left-hand side. So you know very well that this sum over all probability, it should be normalized to 1, right? And this is what we just mentioned. And this is normalization condition of the probability density. And this number 1 has nothing to do with time. It's the universal constant. So as a result, if you take a time derivative of this unity, this number 1, you get 0. As a result, you get 0 on the left-hand side. On the right-hand side, you get minus this. This is the differentiation of this function, j, but you then integrate over the x. So derivatives and integration in your calculus are cancelled, right? Okay, so you end up evaluating this difference between these two boundaries. So this is given by minus j xt. Evaluate these two boundaries, and you take the difference between these two, which is what? Which is j infinity minus j minus infinity. But what is this j infinity and j minus infinity? This, as I mentioned, this wave function should be square integrable, and far away from this origin in this plus infinity direction and also minus infinity point, this wave function should vanish, right? As a result, if you integrate over the entire space, then these two boundary values of this current density, probability current, should be 0. And as a result, the right-hand side of the equation is also 0. So, and this is identity, which tells you that the time change of your probability, the total probability, is actually 0, and which is also true if you calculate this probability current on the right-hand side. This also tells you that you get conservation of matter. Okay, so conservation of current of particle flow. So you could, of course, do a slightly different way to show this continuity equation by partially integrating over the space. You do not just integrate over from minus infinity to plus infinity, but you simply just integrate over a finite range and take this time derivative of that quantity. Suppose you simply just evaluate this time change or time derivative of your particle flow between, say, x equals A and x equals B, and you just count how many particles are flowing through this interface at x equal to A over time and s equal to B. So you simply just integrate over this position between A and B of this probability density. And what you will get is this, which is your probability current evaluated at x equal to A, subtract from J at B. So, which means that this change in the density of your charge, or time change in the density of your particle or charge, is actually given by the net change in your flux. So this is your flux change between these two positions, s equals to A and B. So remember, J refers to this probability current or some kind of flow or flux. Okay? So if you evaluate this probability density inside this volume as a function of time, you simply just take the time derivative of this probability current, probability density inside this tube, and that value is actually the flux change, which means that it is the flux evaluated at x equals to A subtracted from this flux evaluated at x equals to B. Right? So this is exactly what happens when you have some kind of fluid passing by a tube, right? So you simply just measure and see what is the time rate of this water flow or fluid flow per second. And that kind of water flow per second is nothing but this flux between these two positions, difference in flux between these two positions. Okay? And as a result, you get a continuity equation, which says that this probability density change in time is really the change in the matter of flux, in the probability flux. Okay? In other words, this is flux change is really what makes this probability density change in time, which means that you don't get anything disappearance out of the blue and everything comes in must go out. It's a conservation of matter or a conservation of probability. So now let's just evaluate this, define and evaluate the expectation value. Okay, so since we have more rigorous mathematical formulations of the Schrödinger wave function psi, and we define this probability and this probability current, and we should be able to evaluate all these observables such as position, the momentum, and so on and so forth, and energy. But let's just define the way we calculate this expression value in quantum mechanics. So there is a bracket like this on the left. On the right side of this, any physical observables, which I call this f of x. In quantum mechanics, this should be an operator wearing a hat. So we calculate the expression value since, as I mentioned, each time, each measurement at each given experiment for a particular quantum mechanical operator, such as momentum, energy, and so on, you may get a different answer. Okay, so one measurement, one answer. A second measurement, a second answer, the first answer is not necessarily the same as the second answer. Okay, so this is quantum mechanics, and this is precisely where we introduce the probability distribution. Okay, because there is a certain probability for you to measure a certain observables to be at, say, position 1 or position 2 or momentum 1 or momentum 2, and so we don't know beforehand so-called the correct position of momentum is until you measure it. Okay, but each time you measure, you may come up with different values, but different value could be found at a different probability. Okay, and that's why you need to take the expectation value. So suppose you take the 100,000 millions measurements, and each measurement you may find a different answer. But if you take repeatedly take many measurements like this, and you may have so-called the average value or expectation value of certain quantum mechanical observables f of x, and this is given by this integral. So this is very similar to what we're familiar with when we throw the dice. There are 6 faces of a cube, right? So labeled by 1, 2, 3, 4, 5, and 6. So each time you throw a dice, the dice would tell you a particular number each time you throw a dice, say number 4, and so on and so forth. And so one calculate what is the expectation value when you throw a dice, say 100 times, for example. So, and of course the expectation value in your high school mathematics tells you that you should do this way, right? So you should multiply the number 1 by the probability that you find the dice to be at number 1, and plus 2 times the probability that the dice shows up at number 2, and so on and so forth, plus 3 times the probability that you find the dice to be at 3, and 4 times the probability for 4, and 5 times the probability at 5, and 6 times the probability at 6, right? So this is your high school mathematics, and here we are doing pretty much the same thing, except we have many different eigenvalues or phases of a cube, and they are described by this probability density or the probability distributions. So whenever you take the measurement, you must multiply by this probability, and you sum over all such possibilities. Okay, which means that you integrate over the entire space, and the integrand is the function f of x times this probability density distributions. When we've done so, this is the definition of the expectation value of any quantum mechanical measurement, but conventionally we should separate this psi star from psi for the reasons that we will see later. Okay, so you know this p is like psi squared, which is psi star psi, right? But you don't simply just put this here on the same side. You should really move this psi star to the left of this f of x function, and this psi should remain on the right. Okay, so in other words, you should sandwich this f of x by psi of x t on the right and psi star on the left. And this is, convention to avoid any incorrect evaluation of the expression value, in particular involving the derivative of x, which we'll discuss in just a moment. So this f of x is any quantum mechanical operator you can imagine. So the simplest possible operator is the position operator. And so you could plug in the definition of this expression value of the position of a quantum particle which is nothing but this, right? Which is really what you expect from the probability theory. Or so the expectation value of position of a quantum particle can be calculated through this integral that you insert x in the middle between psi star on the left and psi on the right, and you integrate over the entire space. And so if you already solve this psi, the Schrödinger wave functions from the Schrödinger equation, and you are done. And the remaining job is just to evaluate this integral to get the expression value of x. So likewise, if this f of x is not just x, but is, say, momentum, but of course the momentum operator is a function of x, which we'll derive later, but this expression value of the momentum variable follows the same way that we evaluate the position. However, as we'll see later, that momentum operator in quantum mechanics is equivalent to taking this spatial derivative, partial derivative, dx multiplied by minus IH bar, and this involves taking the derivative of this function vector x. And this is precisely what I mean by this convention, that we need to put this psi star on the left and psi on the right to get the correct evaluation of this momentum variables. Okay, so, and let's take a short break. When we come back, we will start to evaluate this momentum average or expression value of the momentum operator following this definition. Okay, so let's continue calculating this expression value of a momentum operator. As I mentioned, this momentum operator is a very important quantum mechanical operator, but it is also a function of position x, because from the classical mechanics we know that this momentum p is given by this mass of a particle times the velocity, right? Well, what is velocity? Velocity is given by dx dt, right, in classical mechanics. So we should also use this kind of definition in quantum mechanics, that somehow, although this momentum is an operator, but it is related to this position operator in such a way, but we need to really put the expression value on both sides to make it really a quantum mechanical identity. Okay? Because we need to take the expression value of x and p and to see this equivalence. And this is the equivalence that we expect, and it should be satisfied, but we need to derive this equivalence. So, and as a result, we should interpret this expression value of the momentum operator as the mass times the expression value of x dt, which is the sort of average velocity. And then you know what this expression value of x is. This is nothing but this integral that we just defined. And the only thing that you need to do is to take a time derivative of that integral, right? And let's do it. So if you take a time derivative of that function, you should have two contributions, right? Okay. So one is the partial time derivative psi star, and another is psi. So x is x. So x is independent variable from time, so it has no contributions to this time derivative here. So you got only two contributions. One is this partial psi star, partial t. Another is partial psi, partial t. Okay, so now it's time to take advantage of the Schrödinger equation. So you know this Schrödinger equation is about time derivative, partial time derivative of your Schrödinger wave functions and the Hamiltonian operator. So you simply just plug in the Schrödinger equations, and on the left hand side you get partial psi, partial t, but on the right hand side it is the second derivative, space derivative of Schrödinger wave functions. And in particular, for free particles, there's no potential. So you don't worry about this potential term. So you just have the second space derivative of psi star as the first term, and partial square psi, partial x squared as second term. And there's a minus sign in between. And of course, it's h bar over 2I as a prefactor if you plug in the Schrödinger equations for this and for that. So now you try to manipulate these two terms and simplify this two terms. So the first term is given by this combination inside the integral, and you could play some mathematical tricks by adding and subtracting the same term, and you could express this in terms of some kind of total derivative of some combined function, say this combination. And of course, by doing so, you must add and subtract the same term, and these are the terms that you need to add and subtract. So this is nothing difficult because this is just by chain rules. Okay? So by chain rules, there's nothing but this chain rules, and so you apply the chain rules in your calculus, and you just make such a derivative of such a combined function of x like this, and for the purpose that we'll discuss just a moment. And then you could subtract these two terms like this, and when you have done so, you get this stuff inside the bracket, and plus some extra terms on the right. And because the yellow bracket, outside of the yellow bracket, there's a space, a derivative partial x, but then you should cancel by integration dx like this. And as I mentioned earlier, that this differentiation is canceled by the integration. So at the end of the day, so this yellow bracket thing inside this integral becomes just a difference between its endpoint values. So let me just point out that this term becomes a surface term. This is called the surface term or boundary term, because when you cancel this differentiation by this integrations, you get at the end of the day just a difference between the boundary values or the surface term. The difference, the surface term, which means that the whole thing inside the yellow bracket evaluated at plus or minus infinity. But as we just defined earlier, that any Schrödinger wave functions should be square integrable, right? So which means that this wave function should vanish at plus or minus infinity. As a result, this whole thing evaluated at plus or minus infinity are both zero, and this term go away because it's square integrable. Okay, so then we simply just have to deal with the remaining term right there. And so let me just summarize this expression value of the momentum operator, and which is nothing but this integral and this is the definition of the momentum operator in terms of the differentiation of a wave function in real space. So quantum mechanically, since we know that if we evaluate this expression value of the momentum operator, you should evaluate this way. And you could just take an abbreviation of this momentum operator by removing all these integrations and psi star and psi, and just extract the essence of this momentum operator. As an operator, this operates like this. So this qualifies the definition of the operator. Yeah, so let me just repeat. When you take the expression value of the momentum operator, this is what you should do, right? So you should evaluate the integral, but inside the integral, this yellow box is the most important part of this expression, and this says that you need to take differentiation of the wave function on the right with respect to x and multiply by h power of I, and then on the left you multiply by psi star, and then you integrate over the entire space. And this is this p expression value, and you could just remove this both sides of the expression, just focus on this yellow box, and you could simply just say that p operator as a quantum mechanical operator take this form, that it equivalently it evaluates this differentiation of the wave function to this right with respect to x. And this is what we call this operation. You need to operate. You need to do something onto the wave function. So what do you need to do? Well, you need to take differentiation, and this is the operation. The operation is that you need to take differentiation of wave function with respect to x. So that's precisely the meaning of the operator. The operator operates onto this wave function. So, and this is the first non-trivial quantum mechanical operator that we find when we evaluate the expression value of momentum. Great. So then we could follow the same logic, and we could define this any observables that we could evaluate this expression value following the same type of definition. However, as we mentioned, that this observables could be also a function of momentum, right? And also a momentum operator. And we also know that there is a Fourier transformations taking us between psi of x and phi p, where phi p is the wave function in momentum space. So the wave function in the real space, or Schrödinger wave functions, is related to the wave function's momentum space. Again, so we should derive the interpretation of the momentum space wave function, psi p, as a probability distributions of finding the particle at the momentum p, right? So, and then we could define the same type of expression value in momentum space. Just like what we define the expression value in real space, we could also define this f of p like this. So, which means that we could use basis, either the real space or momentum space, as a basis to evaluate the expression value of any quantum mechanical operator. Meaning, we can express any quantum mechanical operators in terms of either x or p, whichever is convenient for us. Okay? And we'll show later that these two representations, either in real space or in momentum space, are completely equivalent. So let's take a short break. When we come back, we will see this kind of a correspondence between x and p. So let's continue. So before we establish this equivalence between this evaluation of expression value in real space and momentum space, so let's just generalize such a expression value that we just mentioned, which means that this momentum variable, when we take the expression value of the momentum variable, we should insert this h bar of I partial x in the middle between this psi star and psi. But in general, if we want to evaluate any functions of momentum, for example, it's p squared or p cubic or whatever functions of p, and it's very easy. You simply just replace p in the integral on the right-hand side of the equation by h bar of I times partial x. For example, if you would like to evaluate p squared, expression value of the p squared, which is nothing but this. And remember, when you take this differentiation, you only take the partial derivative to the right of that momentum operator. And you do not take partial derivative for this on the left. And that's the reason why we separate this psi star from psi, and so on and so forth. Okay, so, but then we need to really show that this expression value is a real value, because you may worry that this kind of expression value carrying a same I or minus I here may lead to complex results, which should not happen, because we know that any physical observable should be real valued. If you want to measure this momentum of a quantum particle, expression value of the momentum, it certainly should be real valued. The complex valued momentum makes no physical sense. But we should worry that this imaginary number I may mess things up. But don't worry, we need to prove that even though there is an imaginary number I here, when we take this expression value of the momentum operator, certainly it should give us a real value. And the proof could be go from two ways. So first, we can show that suppose this expression value of the momentum operator is a complex number, and if you simply just subtract this p from this p star expression value, suppose this is 0, it certainly tells you that p is real. Otherwise, it will give you an imaginary number, right? Say if this p is actually a plus ib, and p star should be a minus ib. So if you subtract these two complex numbers, you get 2ib, which is non-zero. And this is the good test to check whether this p expression value is really a real value or a complex value. Okay? And of course, the final answer is that this subtraction gives you 0. So you don't need to worry about this complex expression value of the momentum operator. But the reason why this vanishes needs some calculations. So let's just plug in this definition of the expression value of the momentum and subtract one from another. Remember, when you take the complex conjugation of this expression value of the momentum operator, you should convert all this I to minus I and so on and so forth. And that's why you get this minus sign. So let's just take subtraction. You see this, there's a minus sign here, minus sign there, and a double minus 1 is actually plus 1. So you get a summation. Okay, so then you simply just sum over these two terms, and by chain rules, this is nothing but the partial x derivative of this, the whole thing, psi star times psi. By chain rules, you could verify easily that this leads to these two terms. But again, this is a surface term. Remember, we should take advantage of the square integrable properties of Schrödinger wave functions many, many times. And this is an example, very good example, that you can see that this cancellation between this derivative that's integral. So at the end of this cancellation, you get simply just the m point values of this psi star psi. And you subtract this m point value between plus infinity and minus infinity. But if you know that for square integrable Schrödinger wave functions, both n values should vanish. 0 minus 0, which is 0. And the reason why this vanishes is because it's square integrable for psi. Okay? So very beautiful check. So we confirm that even though there seems to be an imaginary number appearing in the momentum operator, when we take the expression value of the momentum operator, it certainly gives us a real number. It's not a complex number because the surface term certainly vanishes. Okay, so but we could just use the second approach to confirm this real values expression of momentum operator by saying that if psi is periodic but not square integrable, even if this psi is not square integrable, we could also show that this expression of the p should be real. Okay, as long as this psi is a periodic function, meaning that if you shift this position x by some period capital L, and this psi x plus L is the same as psi of x, which means that this is periodic. If this is periodic, and I could simply just again evaluate this difference, but we integrate over this entire period, again you end up getting this difference between this psi square evaluated endpoints. But this psi L is the same as psi 0 found in this periodic condition. As a result, even if they are not square integrable functions, so as long as they are periodic, and we could show that this is also a real value expression of a momentum operator. So we can define this so-called Hamiltonian operator for a free and also interacting particles in the following way. So remember, this is the Schrödinger equation, and we could just use a shorthand notation by defining Hamiltonian operator, which I call this H wearing a hat, which is certainly an operator in quantum mechanics because P as a momentum operator in quantum mechanics is the operator, right? Okay, so the P square is also the operator. So this H wearing a hat is defined as the Hamiltonian operator in quantum mechanics, which is the quantum mechanical operator for a total energy. For a quantum mechanical system, when you try to evaluate the total energy, you must evaluate the expression value of the Hamiltonian operator. So when you evaluate the expression value of the Hamiltonian operator, this leads to the total energy of your system, which is a sum of the expression value of the kinetic energy plus expression value of the potential energy. Okay, so again, since the energy is this quantity that you can measure in the lab, in the laboratory, so this must be real. Okay? As a result, this Hamiltonian operator must be so-called Hermitian. So we will define the Hermitian operator later, but this just tells you that if you take the Hermitian conjugate or a complex conjugate of this operator, you get the same operator, and if you find these properties, we call this Hermitian. So we will define that later. For a Hermitian operator, the expression value should be always real. Okay, so we haven't finished this yet, but we will a week after next week. You could start to read chapter 2 and try to understand all these equations that I defined today. And for those of you who are already taken modern physics, so this is a piece of cake, and you should understand in a deeper way that you know both the mathematics and the physical interpretations of what you're calculating. So next time, we will formally establish such an equivalence between these two operators. Say X operator in momentum space is given by this operator, and this is the corresponding operator for the momentum operator that's expressed in real space. Okay, so you could evaluate any quantum mechanical operator in either real space or momentum space. Okay, so you can evaluate the momentum operator in real space, and you should follow this. But if you want to calculate this anything in the momentum space, you should follow this. And next time we will establish such a correspondence between X-based operators and the momentum-based operators. And also we will derive this commutation relations between X and P operators. Okay, so that's enough for today. Okay, so I will see you a week after next week. Okay, so if there's no further questions, I will see you 10 days.